The system type actually depends on the value of or the power of the integration. So if you have s in the denominator, so as we said here, the value of s here, which is the pole at the origin, or we call it sometimes we call it integration. So the value of s or the power of s will indicate the type of the system. So based on what is the value of n, so we can decide the type of our system. So as you can see here, this is the open loop transfer function, which consists from 0, 0, 1, 0, 2, and so on, factors of zeros and the factors of pools here. So we have s to the power of n. So this n can change from 0 to any number here. Okay, so the first value of n 0. If the value of n is 0, that means s to the power of 0 will be 1. So we do not have any zeros at the origin value. So in this case, we call our system is type 0. If n equal to 0, our system is type 0. If we have s, 1s for example, so the transfer function become s plus 1 for example, s plus 2 or s plus 3 and so on. So we have one s here, so this system we call it system type 1. If we have s square, so this system we call it system type 2. Actually, you need to differentiate. This is the most important part of steady state error calculation. You need to differentiate between three types of inputs, which is step function, parabola function, and ramp function and parabola function. You need to differentiate between three type of system. So you have system type 0, system type 1, system type 2, and you need to differentiate between three constants. Later on, these constants depends on the input function, and this constant actually as we already previously mentioned, so one is we call it one is related to the position constant, the second is related to velocity constant, the third is related to the acceleration constant. We already mentioned this position and velocity and acceleration when we talk about the type of the input and which system is preferred to, or which input is preferred for each application. Okay, so if you can differentiate between these three, so you can know how to calculate the value of a steady state error for each situation or for each case. So the first case here, which is case A, actually we have three cases: case A, case B, case C. So for case A, our input function is Rs equal to 1 over S. So this is the step function. Step function input, which is ut, and its Laplace transform is 1 over S. Okay, so this is the first case. If you apply for your system input a step function with 1 over S, that means you are going to increase the poles of your system by 1, because you have 1 over S. That means you will add one pole. This is pole actually. Even that you have a GS, it has the GS is there. The GS, it has its own poles, which is, we call it natural response, will generate the natural response. It has its own poles from the component. We apply also 1 over S here to the input. So we are going to increase the number of poles by 1. Okay, and we have one pole at the origin. I don't know how many poles they have in GS. This depends on the type of the system. But if I use the step function, that means I'm going to increase the number of poles by 1. If I use the ramp function, I will increase by 2 because I have 1 over S squared. If I use the parabola function, so I'm going to increase the poles by 3, so it's become 1 over, because 1 over S cubic. Okay, so now let us focus on the first case, which is the the pole at origin. We have only one pole for the input of the step function. So if you want to calculate the error for this case, when you have the input is 1, we need to use the formula that we learned before. This formula said ES equal to 1 over R or equal to RS over 1 plus GS. So the function or the formula said ES, this we already learned how to calculate the error from the open loop transfer function. Now forget about the closed loop transfer function that we used in the first example. Now our focus all on the open loop. So ES equal to RS over 1 plus GS. This is the formula to calculate the error of our system. So now I have the input RS equal to 1 over S. You just substitute for RS by its value. So it's become like 1 over S over 1 plus GS. Whatever is the value of GS. This is the derivative for all GS. Any system, any GS, you can just substitute here. But the input is 1 over S. Okay? For this case. Now, if you want to find the steady state error, which is ESS, will equal to limit, this is also the formula that we mentioned before, S goes to 0, SES. Okay, so this is the general formula to find the steady state error. Now we are going to substitute the value of ES only S times, or just limit. This will equal to the limit of our system. So equal to limit S goes to 0, S times ES. What is the value of ES? It is here. 1 over S over 1 plus GS. Okay? So this is the value of the steady state error that we want to find. Now, if you have S times 1 over S, this S will go with that S. So the formula become limit S goes to 0, 1 over 1 plus GS. Okay, so now if I just distribute the limit here on this one, so limit for 1, no, there is no S, so it's become 1, stay 1. Limit for 1 also stay 1 because no S here. I'm going to substitute the limit only will affect the value of the transfer function. Limit S goes to 0, GS. Okay, now this formula here or this value which is ESS will equal to 1 over 1 plus limit S goes to 0 GSS. It will give you the steady state error when your input is 1 over S. Okay, for any GS, for any transfer function. So based on the type of the system for transfer function, this value will be changed. So if the system is type 0, that means it has one S here in the denominator. If the system is type 1, so it has, 0, no S. If system type 1, it has one S. If system type 2, it will have S square and so on. This formula, limit S goes to 0 for to GS, we call it the static position error constant, which is Kp. Okay, so this we substitute by 1 over 1 plus Kp. From now, if you have input of 1 over S, you need just to find the value of Kp. Then you substitute Kp here, you are going to find the steady state error for your system. Okay, now we have different value for Kp. For Kp depends on the type of the system. So you can see here, if the system is type 0, system type 0, that means it does not have any S in the denominator. There is no S here. You have S plus 1, S plus 3, S plus 5, and so on, but there is no S alone. If there is no S alone, that means when you find the limit for this function, limit S goes to 0, there is no S here. If there is no S, that means no, we will have some value here. So for example, S plus 1 will be 0 plus 1, so it will be 1. S plus 3, it will be 0 plus 3, so it will be 3. So it will give you a finite number. Okay, assume that your transfer function is GS. If it is type 0, so GS, for example, equal to S plus 1, this is just example, S plus 2, S plus 3. So now find the value of Kp. In order to find the value of Kp for this transfer function, Kp will equal to limit s goes to 0, s plus 1 over s plus 2 times s plus 3. Substitute for each s by 0, so you have 1 over here 2, here 3, that means 1 over 6. So the value of Kp in this case will be finite number. It can be 1 over 6, 1 over 10, 1 over 100. So the value of the Kb here is a finite number or a constant. So the value of the error here will become 1 over 1 plus Kb. You substitute for the value of Kb here, it's a number, so you will get finite number also. Okay, if the value of Kb is constant, you are going to get a finite number for the error. So the error will be a value. So you can say the difference between the input and the output is equal to 0.5, is equal to 10, is equal to 100, depends on what is the value of Kb here, and which depends on the value of the GS. This is in the case of n equal to 0. If n equal to 1 or more than 1, so your transfer function will become like this one. This is example for system type 1. It will be s plus 1, for example, over s times s plus 2 times s plus 3. For example, this is just example, okay? So now, if you apply the limit for this GS in order to find Kp, we said Kp equal to limit s goes to 0 GS, correct? So you just substitute for GS here, so it's become like this one, limit s goes to 0, s plus 1 is just over s plus 2, s plus 3. Okay, now if s goes to 0, so here 0 plus 1, it will be, for example, 1 over. But if this s equal to 0, whatever is the value here, all the denominator becomes 0. So what you have, the value of Kb in this case equal to 1 over 0 or 100 over 0 or 1000 over 0, it will all give you infinity. So the value of Kb will be infinite number. If the value of Kb is infinite number, you substitute here, so it's become 1 over infinity, so it's become equal to 0. So 0, that means no error, no steady state error, or the value of error equal to 0 means, what means the value of error equal to 0 means the input equal to the response or the system response. So no difference between the set point and the system response. So this is a, I mean, ideal case. That means there is no error. So you give, for example, you give the set point to, or you have set point is equal to 10, your system output equal to 10. So no difference between the set point and the system output. So this is whatever is the value of S. I mean, the type of system, system 1, system 2, system 3, whatever is the value. Since you have one S here, at least one S, so this S will make your denominator equal to 0, make your Kb equal to infinite number, make your error equal to 0. Okay, so this is for the first case, which is the input is 1 over S, or the input is a step function. For the second case, which is the input is equal to 1 over s square, which is ramp function. 1 over s square ramp function, that means you are going to have 2 extra bulls to your system. Okay, so this is, you substitute for es by the value of 1 over s square. So this is the formula, become 1 over s square over 1 plus gs. Okay, in order to find steady state error, this is the formula, s times es. When you multiply s by s square here, this is the formula, limit s goes to 0, s 1 over s square, because we have system, the input is ramp function, so the s square will go with this s. We still have one s there. Okay, so this one s will goes down to the denominator, so it's become like this, limit s goes to 0, s plus sgs. If you take the limit to inside, it will not affect the one, because there is no s, the one become 1, still 1. If you take the limit to down, so you have limit s goes to 0 for s, so s will be 0, so the is 0 value, plus limit s goes to 0 for s times gs. So this is the second constant that we mentioned before. We said we have 3 constants. The first one, we call it the position constant, and here we call it the static velocity constant. static velocity error constant, okay, which is the value which we call it kv. The previous one is it was kp, position, related to position, here related to the velocity. Okay, so now your steady state error here equal to 1 over limit sgs, which equal to 1 over kv. So if you have the input 1 over s square, your steady state error will equal to 1 over kv, and your kv will equal to limit s goes to 0 sgs. Okay, here s limit s goes to 0 for sgs. Whatever is the value of gs, you are going to multiply by s, you find kv, then you find the value of the error. So as you can see here, if your system is type 0 means your transfer function, as we said before, there is no integration, there is no s alone. So it's like s plus 1, s plus 2, here s plus 3, for example, for the numerator. Okay, so if this your transfer function, so this same is this system is type 0, so you are going to substitute for to find kv will limit s type, for example, this will make kv equal to limit s goes to 0 s times gs, this is gs, s plus 3 over s plus 1 s plus 2. Okay, so now there is no s here because the system is type 0. This s will stay there. If this s stay there, that means you substitute for s by 0, all value of kv become 0. If the value of kv equal to 0, the value of error will equal to 1 over kv equal to 1 over 0, so it's become infinity. So in this case, the value of error is very big. Okay, so if your system is type 0 and your input test function is the ramp function, which is 1 over s square, your error will be infinity in this case. But if the system is type 1, so if the system is type 1, that means you have s here. If you have s here, you will have s in this point. If you have s here, this s will goes with that s. So you still have s plus 3, s plus 1, s plus 2. You substitute each s by 0. You will have 3 over 1 times 2. So it will be 3 over 2. So this is a constant. If the value of kv is constant, the value of error also will be 1 over constant, will give you a constant. Constant or finite number, here also constant or finite number. This is in the case of system is type 1. In the case of system type 2 or 3 or 5 or 100, that means you will have more than one s in the denominator. If you have more than one s in the denominator, in this case, you will just remove one of your s and the rest will be stay there. So for example, here you have the transfer function s plus 2 over s square. This is system type 2. S plus 1, s plus 2. Okay, now when you multiply by s here, this is s times this s square. It means like this one, s times this s square, or s plus 2 over s square. The square will go with s. We still have one s in the denominator. If you still have one s in the denominator here, and you put this s equal to 0 because you want to apply the formula s goes to 0, that means your denominator become 0. And the numerator is a constant, which for example 2, so 2 over 0, it will be infinity. If the value of kv here equal to infinity, that means the 1 over kv will equal to 1 over infinity, so it becomes 0. So the steady state error in this case will equal to 0. So the better for the system type 2 and above. If you have system type 2, system type 3, and so on, so it will give you infinite value for kv, but it will give you 0 value for the steady state error. Okay, so in this case, this is the best for the system type 2 and above if you have the input of your system is 1 over s square or ramp function. The third case, that you have your input is 1 over s cubic. We said we have three inputs. Three inputs means the first input was 1 over s, and it gave you the first constant, which is kp. Okay, and the three type of system, we said type 0, type 1, type 2, and we already test for the three type of the system. The second case was the input is ramp function, which is 1 over s square, and it gave us the constant, we call it kv, and we calculate the steady state error based on the kv. Here the steady state error in the first case, we said 1 over 1 plus kp. Here 1 over kv. Now we have the input is 1 over s cubic, and this gave us the value of or the constant, we call it ka, which is related to the acceleration error constant. Okay, static acceleration error constant, and the value of the for the error in this case also is equal to 1 over ka. As you can see here, you just substitute for the value of rs, 1 over s cubic, and then substitute for the error function here, which is s times es. So the s here will goes with 1s from this one. We still have 1 over s square. So s square will go down, so it's become s square. It's become s square. When you go, you take the limit to inside, so the 1 stay 1, the s square becomes 0, and the limit goes with the s square here, so it gives you this value. So here this represents the value of ka. We call it ka is equal to limit s goes to 0, s square gs, whatever is the value of gs. Then your accelerometer, I mean with your error, will become 1 over ka, as you can see here. How to calculate ka? This is how to calculate ka. Based on the value of gs, we are going to calculate the value of ka. Based on the type of the system, we are going to find the different value for our ka. So we have three type of systems. System type 0. If the system is type 0, means you have gs equal to s plus 3 over s plus 1 times s plus 5. For example, here this is system type 0. If the system is type 0, you want to find the value of kv, I mean ka here, accelerometer constant. Ka is equal to limit s goes to 0, s square times gs. Correct? So whatever is the value of gs, since you have s square here, so for sure the answer will become 0. For system type 1, this is for system type 0, the answer becomes 0, so the error will become infinity here, because the error is equal to 1 over 0, so 1 over 0 will give you infinity. The second case, system type 1, if the system is type 1, that means you have 1s here. If you have 1s here, so this 1s become like this one, ka will equal to limit s goes to 0, s square times s plus 3 over s plus 1, s plus 5. So this s will goes with that square, but we still have one s here. So this s goes to 0, so all ka will give you 0. For system type 1, it is the same as system type 0. You still have ka equal to 0. If ka equal to 0, that means your, sorry, that means your output or your error will still equal to infinity. Okay, so the error in the second case also is still equal to infinity. The third value or the third case, if your system has n equal to 2, that means system is type 2. In the case of system type 2, this becomes square, for example. If that one becomes square, so you have here ka will equal to limit s goes to 0, then you have s square times s plus 3 over s square, because it is times if the system is type 2 here, s plus 1, s plus 5. Okay, so this s square will go with this s square, so we do not have any more s integration in the denominator. Okay, so we will not get the value. I mean, we do not have also s integration in the numerator here. I mean, sorry, s in the numerator. So no s in the numerator, no s integration in the denominator. So the value here we are going to take, for example, 3. For example, in this example, 3. Then s plus 1 would be 1. S plus 5 will be 5. 1 times 5 it will be 5. So it gives you constant number or finite number. For that, for the system type 2, Ka will be constant. Then if you have 1 over constant, it will give you also constant or finite number. So the system type 2 will give you constant value. For the Ka, those you have a constant value or defined value for the error. It's not infinity like the previous two cases. Infinity means very big, so it's not good. That means your system will not give you will not reach to the state to the state a good value of steady state error. Okay, the error is still very big. Then we need to consider one more case here. If the system is type 3, if the system type 3, that means you have s square and you have here s cubic. So you still have one s in the denominator. After you remove f square with the cubic, you still have one s here. So in this case, if you have s in the denominator, the value of the Ka will become infinity because this is 0. Number over 0 will give you the infinity. Okay. If the value of K equal to infinity, the value of error steady state error equal to 1 over infinity, which is 0, which is the best value. So in this case, the error becomes 0. So no error, no difference between the set point and the response of our system. So the steady state error value is equal to 0. So actually all these cases with the different input values or input function or input waveform with the different constants, which is Ka, I mean Kb, Kv, Ka, with the different system type 0, type 1, type 2 can be found in this table. So in this table here, you have the different values for our system, different input, step function, ramp function, parabola function. You have the steady state formula for each one. So in the first formula will be 1 over 1 plus Kb. The second formula 1 over Kv, 1 over Ka. Then you have for the different system type 0, type 1, type 2. So if you read this slide and you understand the relation between the different three inputs, the different three constant, the different three type of system, it's easy for you to calculate the value of steady state error for any control system. Okay, so this is the summary of the steady state error calculation for this in this chapter.